Students, now we come to lecture 7 of unit 1. In lecture 6, we had studied mean effective pressure. I have gathered some points which you should know before we come to the topic. Now, some facts about brake mean effective torque. Brake mean effective pressure produces the brake mean effective torque. For any internal combustion engine, the maximum BMP is obtained at full load for a particular engine speed. So when will you get the full maximum BMP, mean effective pressure, brake mean effective pressure? At full load. Second point to note, throttling the engine decreases the BMP due to higher pumping loss. When you're accelerating, pumping losses increase and therefore the BMP also decreases. For a fixed engine displacement, the engine displacement is fixed, it is VD. If we increase the BMEP, we produce more effective torque at the crankshaft. Means for a fixed size of engine, if we increase the BMEP, the torque will also proportionately increase at the crankshaft. A brake means at the crankshaft. For the same value of the BMEP, a 2-stroke internal combustion engine has nearly double torque compared to a 4-stroke engine because it has only 2 revolutions compared to 2 full revolutions of a 4-stroke compared to only 1 full revolution of a this thing. But this is only in theory. Practically, it is not so. The higher the brake mean effective pressure, the higher the mechanical and thermal stresses on the engine components. And that is why invariably the diesel engine is built more sturdy, it is heavier for the same power output because it has a higher CR. Also, the higher the BMP, the higher the mechanical, the thermal and mechanical stresses will increase. That's why the engine needs to be very sturdy. And the diesel engine is always more sturdy than a petrol engine. So, these points I have made for you to keep in mind. Now we come to the final topic of Unit 1, the difference between the actual and ideal diesel cycle. Now on the chart, this is the ideal cycle and this is the real cycle on the PV diagram. In an ideal diesel cycle, there are a lot of assumptions. So it differs from an actual diesel cycle. A lot of assumptions are made while making the theoretical PV diagram in ideal conditions. The ideal diesel cycle does not occur, this never occurs, and there are many losses in each process. There are so many processes which we have studied. In each process there are losses. We will come to that. For an actual cycle, the shape of the PV diagram is similar, almost somewhat similar to the ideal, but the area, the work area enclosed, this is the work area enclosed by the PV diagram is always less. This area will always be less for the actual compared to the ideal cycle. This area will always be more than this area. From this area has to be subtracted. We have studied that. The assumptions for ideal cycle are, what are those assumptions? First of all, in the ideal cycle is closed. This is in fact the largest difference between the diagrams is simplification of the intake and exhaust stroke. In the exhaust stroke, heat out is ejected to the environment, but actually it is ejected from the engine in real cycles. In the real cycle, burnt gases leave the engine and is replaced by a new mixture of air and fuel. Whereas in the ideal, it's a closed, that means the same keeps repeating, fluid and air keeps repeating, that is the assumption made. Isobaric heat addition. It is never isobaric in real engines. Constant pressure, it's impossible to achieve constant pressure. Heat addition. No heat transfer. There is no heat transfer in an ideal cycle. Compression. In compression, the gas is compressed adiabatically from state 1 to 2. In real engines, there are always some inefficiencies. There are inefficiencies that reduce the thermal efficiency. You can see? And this will be smaller, 1 to 2. That reduce the thermal efficiency. Expansion, no heat transfer. Even in expansion, the gas expands adiabatically from state 3 to 4, which is never the case for a real cycle. Number 4, complete combustion of the mixture. It is assumed that whatever air-fuel mixture is put into the cylinder, it completely burns, which is not so. Some fuel mixture always is retained in the cylinder when the fresh charge is put in. That's where the volumetric efficiency comes in, when volumetric efficiency depends on the exhaust valves. The exhaust valves, there's a limit to the size of the exhaust valve and there's a limit to the size of the intake valve depending upon the diameter of the engine. So it's a restricted passage, and during that time interval, the complete burnt charges don't go out, and the inlet charge which has come in, the air and fuel mixture, some of it is still is thrown out of the exhaust. No pumping work. The fifth assumption which is made for an ideal cycle is there is no pumping work. What is pumping work? Is the difference between work done during exhaust stroke and work done during the intake stroke. In real cycles, there is a pressure difference between exhaust and inlet pressures. Inlet pressure may be a turbocharger or supercharger which is throwing air into the cylinder. This is a different pressure, and the exhaust, after the burnt gases are exhausted, that pressure is different. Here it is assumed that there is no pumping work, it's same. No blowdown loss is the 6th point. Blowdown loss is caused by the early opening of the exhaust valves, which I spoke about earlier. Early opening, and certain amount of the fresh charge invariably goes out of the exhaust valve. This results, so naturally there will be a loss of power compared to the real cycle. This results in a loss of work output during the expansion stroke. No blow-by loss. What is blow-by? Blow-by is when the burnt gases or even the air-fuel mixture, they cross from the side of the piston through the rings into the sump. That is blow-by. Blow-by is around 5 to 10% in new vehicles, new engines, and can go right up to 15 to 20% as we keep running the engine. The blow-by loss is caused by the leakage of compressed gases through the piston rings and other ceramics, as I mentioned. And this is for this reason. The oil change, the engine oil change is changed every 10, 15,000. They are good oils these days, synthetic oils. where they even say you can change it after 15,000. And whereas the oil in the gearbox is changed after 40,000. The reason is that the engine oil gets contaminated by blow-by. In fact, my car, which is a Ford, they say that there is the gearbox oil lasts forever. There is no need to change for the entire life of the vehicle. Here, again in the real cycle, it is assumed that there are no frictional losses, and we know there is so much of rubbing, so much of movement of parts up and down, that there are bound to be losses due to friction. Excuse me. These assumptions and losses lead to the fact that the enclosed area work of the PV diagram for an actual engine is significantly smaller than the size of the area, that is the work enclosed by the PV diagram of the ideal cycle, which we mentioned at the start of this lecture. Repeated. In other words, the ideal engine cycle will overestimate the net work, and because of these assumptions, and if the engine runs at the same speed, greater power produced by the actual engine by around 20%. That means the ideal cycle will produce about 20% more power than the actual cycle. The ideal cycle is never there. This is for the diesel engine, and it is almost the same for auto engines, that is the petrol engines. With this, we come to the end of Unit 1. In the next lecture, we will start with Unit 2 as per the syllabus mentioned in the unit. Thank you.